So today we're going to talk about something a little bit different, more of an algorithms lecture than anything else, actually, not a systems lecture. And reminder, when we get together next week, we're basically moving the course back to hardware for a little bit. So Kunle is going to take over next week. We're going to talk about cache coherence, I think is the next lecture. Is that right?
Yeah.
No, sorry, you're going to do Spark. Sorry, actually, you're going to do Spark first. Yeah. Yeah, because it follows the, yeah. Okay, so sorry, we're not going to actually talk about hardware just yet. But Kunle will be lecturing next time. Okay, so, but everybody's doing okay? All right, let's kind of get to it then. So this lecture, sometimes like people come up to me and go, I've never thought about things that way. So what we're going to talk about today, about everything in the course so far, has been thinking about parallel computation in terms of threads, or in terms of a very, very simple sort of organization of let's do something to every piece of data in an array. That's basically all we've done so far, is I've given you arrays of stuff and you've essentially performed a loop body on those arrays, or you've thought about, okay, I'm going to create these threads and this is what this thread is going to do. So today I want to elaborate on and go into more detail about this way of thinking of I have a big array and we're going to do something for everything on the array. Except instead of just run a function on every element of array, we're going to start expressing computation in terms of a richer set of primitives on arrays or collections of data. Okay? So first of all, just to ground this, remember last time when we talked about GPUs and I said something about like the total number of execution contexts is about 163,000 on one chip? So that means that you probably want to be working on data sets of at least that size, right? Otherwise, you're not going to get the full complement of parallelism or latency hiding. So hopefully, at this point in the class, I've established that even if you're working on a single chip, you need a lot of parallelism. Like you need to actually be working on programs that have hundreds of thousands or more pieces of parallel things to do. Otherwise, you're going to be in a bit of trouble in actually using these things. So what we're talking about today is not going to be outlandish at all, right? Like, so, like if you're just going to write code for a reasonable sized GPU, we're talking about you got to have parallelism in the 200,000 regime. Okay. All right. So also so far in this course, just a little bit more background, I think that whenever we throw a piece of code up on the board or I ask you to do a programming assignment, step one is almost always, where the heck are the dependencies in my program? Because if I know the dependencies, or equivalently, if I know where there are not dependencies, that's where I'm going to get the parallelism. Right? So here's an example of just like a simple set of expressions, and I just wrote out the fundamental dependencies here in this graph. Like I cannot execute an operation that's a node in that graph until I have executed the prior ones. And then, in part B of your assignment, that's in fact you're understanding dependencies and respecting them. Okay. So everything we're going to do today is about writing code in some operations where we're going to just assume that someone has really good, widely parallel implementations of those operations. So instead of thinking necessarily about the dependencies at a fine grain, I'm just going to say I'm going to try and boil my program, my algorithm, down into calls to these functions. And these functions are known to be written in a manner that they can execute highly, highly parallel. So the thought process is, well, if all my code calls these functions and all these functions are highly parallel, then any of my programs are also highly parallel. That's the basic gist of things. Okay. And you do this all the time, right? For any of you writing NumPy code or pick your favorite tensor language or something like that, you allocate variables like like some big array A or some big array B, and you use operations that are operating on those arrays, those collections, right? Like in this class, in this example, if A, B, and C are these big NumPy vectors, then the operation plus is an operation that you hope is implemented as fast as possible on those two arrays. You don't think about threads, you don't think about dependencies or anything like that. Okay. So I want to just generalize this notion of a NumPy array a little bit. And to give it a name, I'm not going to call it tensors or vectors, because the kind of vector has a specific meaning in C++. I like the term sequences, which I've brought, adopted from other researchers and other colleagues of mine. And so I want you to just think about a sequence as an ordered collection of elements. So it's not a set, it's ordered. And different languages have different data types that basically embody this concept. Like in C++, there's actually a sequence. In Scala, it's lists. In Python, you can use a data frame or a NumPy array. Arguably in PyTorch or TensorFlow, you have tensors. The important thing is that unlike arrays, so in an array, you can just say, I want the element 43 at this position. And you get access to it. Unlike arrays, programs can only access elements of sequences through very specific operations. And that's the big difference, right? So when you write your ISPC code, you write your CUDA code, your C code, if I give you an array, even though you can think about it as for every element in the array do X, you could actually, in your code, you could write A sub I, which means you could access any element at any time. Now we're going to restrict that, right? And the ability to access A at any time is the way you create dependencies that can really blow up your program. You're like, oh, this iteration of the loop accessed A sub I. The next one accessed A sub I again. Maybe there's a dependency there. So we're just not going to let you do that so that your code is free of dependencies. Okay? So let's talk about the first of these specific operations that you are very familiar with. We just didn't really call it as such. So that's an operation called map. Almost every piece of code we've written in this class so far was basically a map. It's taking a function and applying it to every element of an input array to produce an output array. Now, how many people have seen this more functional language syntax, like the A arrow B syntax? Have you seen that? So a couple of people. Has everybody seen it? How many people have not seen it? Okay. So plenty of people have not seen it. So map is a higher order function because it takes input variables. So in this case, the arguments to map are the input array A and maybe B, and its output array B. And map also takes another argument, which is a function. So let's just say the input collection, the input collection is a collection of integers. So then, and now imagine a function that adds 2 to an integer. Okay, so it takes this input an integer, f of x, and it returns x plus 2. So that function has signature int to int, right? Input argument is an integer, the output argument is an integer. So this notation here, this A arrow B, just says it's a function that takes as input something of type A, like an integer, and output something of type B, which in my example here is also an integer. So if we look at the actual signature of the map function, the map function takes 2 arguments. It takes a function, like add 2 to something, which in this case, let's say is in this program, what is my program doing? It's adding 10, So in this case, my function is adding 10. So the function takes an integer to an integer. And so map takes that function, which is integer to integer, plus a sequence of integers, and produces what?
Output sequence.
An output sequence, which is of type sequence of integers. If I gave map a function that took integers to strings and applied it to a collection of integers, what would my output type be? A collection of strings. Right, exactly. So all I'm doing here is this is a functional notation that says map takes 2 arguments. The first argument is a function of A to B. The second argument is a sequence of type A, and the output is a sequence of type B. Okay, so if you take programming languages or a bunch of other classes, you'll see that. And it's not quite so elegant in other languages like C++, but we have all that functionality. Like, okay, there's no actual, like I have a sequence here, which I'm actually representing as an array, and I have a function from the standard library transform, which takes, in some sense, this is a pointer, this is an iterator starting at the beginning of A, and this is A plus 8, so 1, 2, 3, 4, 5. This is the end of the array. So basically, this is just defining a sequence. and it says, please apply the function f to all elements of this sequence and put your results here in pointed to by this iterator. So it's the same idea, just like everything in C++ and a little bit jankier syntax. Okay, a lot more clean in a functional language like Haskell. I have a sequence A. I have a function x, which takes x to x plus 10. And then if I map f onto A, I get a new sequence B. Despite me ripping on C++, I would still write this code. Okay, so here's a question. Now put your head, as the implementer of map. So now you're implementing the map library. Is this something that you feel very confident about being parallel? Right? Absolutely, because by the definition of the function, every invocation of the argument f is parallel. And by the way, f is only given access to individual elements of the array, right? Like f is just x plus 10. The only thing f knows about is x. So there's nothing f can do accidentally, for example, to create a dependency. And not only that, the implementer of f doesn't even have to think about operating on collections. The implementer of f just says, just give me one element and I'll tell you how to process it. And that's a nice, clean way to think, right? Okay. So how would you, let's say I gave you, I told you to implement map, and I said it needs to work on sequences of arbitrary length, and you're going to get some black box function f of x. How would you implement map if you want to do it in parallel? Yeah, go for it. Yeah.
We could use SIMD processing. So if we have like an array. Okay.
Yeah, so you could actually say, if I had like the source to f, I could recompile f in a SIMD mode. That'd be pretty cool. But that SIMD thing is only going to, let's say it's only going to do 8 things at once. So what are you going to do about the fact that I could give you a collection that might have 100,000 things in it?
Multi-thread.
Okay, I could spawn threads. I could spawn I could create a worker pool of threads, and those threads could all call execute this thing. When I first asked the question, I was thinking about is imagine I gave you a C++ function already, a header file. So you didn't necessarily even have to recompile the thing. You would just call f, and you could call it sequentially, or you could spawn a bunch of threads and call it in parallel. In general, like here's my little implementation of map given f onto sequence s would be partition sequence s into p smaller sequences. Let's say if I had p processors or p threads, and for each subsequence si in parallel, sequentially just apply map to produce a partial output. And now I concatenate all the outputs, which is basically like I'm going to create a worker thread pool, and those threads are going to process different elements of the sequence. Nothing too fancy here. Okay. So this is pretty easy. All right. So now let's go to some more interesting operations. Okay. So here's another operation that's extremely important, used all over the place. It's called fold. So fold, if you read that signature, takes a function, and that function f now, instead of taking a to b, takes a pair. Takes an a and a b and produces a b. Okay? So I see people nodding, so that's good. And so fold takes sort of like a starting element b, that's not all that important right now, but it takes that function f and a sequence a and produces what? A single element. I'm having a little bit of a problem here. 1 second. Okay. So if we write this in Scala, here's an example. Fold left takes an A and a B. Yeah, exactly. Yeah. So it takes a sequence of A's, a function that takes an A and a B, produces a B, and then essentially iteratively applies this. So hopefully, just make sure that you can confirm that fold left with the function 10, with the function plus, not the function 10. The function plus takes an A and an A to an A, right? Int and int to an int. So this function is expecting a sequence of integers and produces a single integer as output. And the result is what? The sum of everything in the array. So in this case, fold of 10 on this sequence is 53. Okay. So here's an interesting question. Can you parallelize fold? So I see some disagreement, actually. Some people are like, no way. Other people are, yes, we can.
It's like the first problem of the first lecture. We can do some small sums and then sum the small sums and so on.
Okay, so good point. So we have definitely computed the sum of a bunch of integers in parallel in this class. Absolutely. So anybody, does everybody agree with this? Anybody disagree with this? We have a little bit of disagreement.
We don't know that the function we're being passed is associative. So we don't know that the order in which we apply it will be the same every time. Like if we have a list of true and false and our function is exclusive OR, then we could get...
Right, so if you interpreted my question as, can fold plus be parallelized? Yeah, we can think of some ways to do it. As you pointed out, we've done it. But this is general fold on any arbitrary function f. And we don't know the properties of f. And a parallel implementation, for example, that chopped this sequence up into subsequences, in parallel folded maybe sequentially the subsequences and then folded those results, is not guaranteed to get the same answer unless you know certain properties about f. And in particular, in this case, f needs to be associative. Right? So there's some other versions of fold where you give fold a little bit more information, right? Where you say, well, I'm going to give you a combiner function also. And in this case, the combiner, well, not in this case, the combiner function actually needs to take b to b, right? And so now I can split up my input sequence, do all of these sequential but parallel versions of this. And then on each thread, I'm going to get a single b as output, right? And then I can combine those if I want to. But I've pushed this off to the user a little bit, right? Often it's the case that you care about the f being b to b to b, like the plus operator. And if f is b, a pair of b's to a b, then you basically also can specify f and combine with one function. Does that make sense? And so as long as that f is associative, you can perform a parallel fold by just giving a single f. And the way it will be implemented is that it will apply f, 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 and then it will use f to combine everything. Okay. Note that f does not need to be commutative, right? Because I actually am still doing all, like if I implement it correctly, I'm still doing all the math in the same order. Just needs to be associative. Okay. So all of a sudden, like for some f's, so for some potential f's, like plus, we've got a parallel implementation of this thing. Okay. And now we have the ability to map data in parallel, and we have the ability to do sort of forms of data reduction, sums and averages and stuff like that. Now, there's actually something that's cool that I don't have on the slides or in this lecture, but think about the following. Imagine you wanted to do like a dot product or something like that. So you first had a map, and the map actually took a pair of elements. Or that's a bad example. But imagine you wanted to multiply all numbers by like 10. That's a map, and then compute the sum. Okay. So you would write that in these primitives, right, as map times 10 on the sequence. You get out what? A new sequence. And then you apply fold with the plus operator to compute the sum. Okay. But if I know the definition of these operators and I saw a program that was map and then fold, you could imagine that I could perform a transformation to that function, which turned it into something kind of interesting, right? Like I would turn it into a fold that actually did the multiply by some number, and then immediately folded in the result. So you could start thinking about transformations that I could do that don't actually require two passes over all the data, provided that you know the definition of map and fold. And that's actually what these more sophisticated JIT compilers are actually doing on your PyTorch code and stuff like that, just so you know. Okay, so let me give you another one. So we have fold, which is sequence to scalar. Now let's think about scan. So scan is sequence to sequence for an associated binary operator that takes an A and an A to an A. So let's just kind of simplify it here. Let's just say that operator's plus again. And so what scan computes is the repeated application of that operator up to and including the current element. Okay? So if we look at this result here, the result of scan with the plus operator is the first element of the output is the sum of the all elements up to and including this element in the input. The second element the second element of the output sequence is the sum of all elements up to and including the same position in the input element. Okay? So the last element of the scan is going to be the fold, but now I'm producing all of the partials. So first of all, do you see the difference between fold and scan? Like fold produces a single value, scan gives you all the partials. And if I had to implement scan sequentially, it might look a little bit like this. Like you'd do this in a second. The first element of the output is the first element of the input, and for I equals 0 to n, the output element is the previous output element plus the new input element. So the question is going to be, is this parallel? And things start getting a little bit trickier now. Before we move on, just as a detail, sometimes in some libraries, a scan will be an exclusive scan, and sometimes it will be an inclusive scan. I have inclusive here, which is up to and including the current element. An exclusive scan is up to but not including, so it excludes the current element. If you have an exclusive scan, how do you compute an inclusive scan? Or add in that case, but yeah, exactly. Like you just take the output of the exclusive scan and you would add the current element. Cool. Okay, so you probably have a sense of where we're going here. Now we need to figure out how to parallelize something like scan. All right, so let's think about this a little bit. So, and again, let me get a little bit more formal. Here are two different definitions of scan, inclusive and exclusive. The output element is always just going to be the repeated application of that binary operator to everything that I've gotten to so far, including me. Okay. All right. So ignore my broken build. So let's just think about it. So how would you go about this? This is going to be an inclusive scan, by the way. And like you said, we can always just minus the element if you want the exclusive. So let's think about this. How would you do it? Any thoughts on how you go about it? Yes, sir.
I would start with finding the total sum by doing divide and conquer.
Okay, so you're going to find the total sum. Okay, so, and how you, well, we actually already have a really good implementation of total sum. We know how to do that. Like, you don't even have to do, well, you do divide and conquer onto your threads and add them up. Okay, so let's just say that we have a subroutine that computes the total sum. That's fine. And that would take cost what? That would be basically, if this is of length n, it would be n over number of threads would be the total time, right? Because I would just break the array up into t pieces. Everybody computes a partial sum. I combine the results. Pretty easily parallelizable. So yes, we can do that. Does that help?
I don't think so.
Well, it's a reasonable starting point. But okay, let's keep going. Any other ideas? Yeah.
I was thinking one of the steps you can do is imagine split the sequence up into half and add in the first half. After that could be one step closer.
Okay. So one thing we could do is we could just say, let's just say we magically had the sum of the first half. Is that right? Is that what you're saying? Then if we knew the sum of elements A0 through A7, I could definitely apply that sum to all of these elements in parallel. It's kind of interesting. Yeah.
Perform scan over the subsequence and this before scan return.
Okay, and so basically that's you're just taking this idea of dividing the thing in half, because essentially if we performed a scan over the first half, then we could just take that result and then we add it into the scan results for this half. That's correct. And we could break that up into as many pieces as we want. Yep.
Can I call the first one and the first two, the first three? Sorry, can I call 4 on like A0 and then?
You can do whatever you want. Yeah.
And then that stores the value there.
Yeah, like that fold is basically this way to do the parallel sum, right? Okay, I like this. I think there's some good answers here. What if I make it even harder and say, let's imagine we're running this on a GPU. And I'm going to come back to some of those ideas that you just told me. And we have the same number of threads as we have elements. Let's think about this in the massive parallelism machine. I want a really parallel solution. So let me just start hinting at a few things. What did I do? So I have parallelism that's now, this O of n, and I just added up every neighbor. Now what did I do? So the notation in my slide is a value. I'm showing you the value, like all the values that go into the sum at a current location, right? So after the first step, the sum of A0 and A1 is in the second element. And after the second step, the sum of A0, 1, and 2 is in the second element. Or really, I should look here. After the two steps, the sum of A0 through 3 is there. And if I keep going, at some point, I have my scan. Okay. So first of all, what is if I did a scan sequentially, how much work do I have to do? Remember that C code I just put on the slide? How much work did I do? If the size of the array was n, the cost of the algorithm was? Well then, I just walked down my array. What's the cost of this algorithm in terms of the amount of work done? N log n, right? Because the first step I do n work, or n over 2 work, then I do n over 4 work, and then I do, I don't do n over 4 work. I basically do n over 2 work, and then I do similar work. Yeah, so it's n log n cost. I have O of n work, and I have n steps. Okay. Now, what's the longest chain of sequential steps, which is often something we call span in a parallel algorithm? Like if you had an infinite number of processors, this would take log n time. The total amount of computation you do is n log n. So I'm doing O of n work, n steps. I don't like the fact that I asymptotically increased work that I'm doing. Because if I'm a parallel machine and I have like n is 1,000,000, log n is non-trivial. So it turns out that there's a way, and this is actually a pretty clever algorithm that was came up with a guy, I think this was Guy Blewick that did this, where I can keep my log n span, and I can be more clever and get it in O of n work. Okay. And here's a little bit what the algorithm looks like. And this is something that I think is a lot easier just to stare at on your own. But the gist of this is that there's 2 phases now. There's if you think about there being a combining tree in phase 1 and then like a splatting tree, an inverse tree on phase 2. And if you read documentation of this on the internet, people will say that there's an upsweep phase and a downsweep phase. So the upsweep phase is computing these partial sums in this tree, where kind of to the point that you all were alluding at, look at this. Here is the sum of the second half of the array. Here is the sum of the first half of the array. And then along the way, we've computed some partial sums. So if you look at it, I have the first half here, the second half there, the first half there, and then I still have these interesting partials throughout the result of my combining tree. Okay. And then very much to your point earlier, where you said what we're going to do is we're going to take that partial sum, like the back half of the array, and if we just had some way to apply it to the appropriate elements, or the partial sum from the front half of the array, for that matter, and apply it to the appropriate elements, we could just kind of rebase everything. So look what happens. After you do this upsweep, first of all, we're almost done here. We're done here. And so we take that partial sum and shove it over here. Okay. Now at this step, I just overwrote. And then it basically becomes take your partial sum and bring it back and then propagate it. That's kind of the way the combining tree works. Right? And if you look at this actually only does a total of O of n operations, because the first step is n, the next step is n over 2, the next step is n over 4, and so on and so on. And that telescoping series, as you might know from 161 or something like that, is O of n. Right? Now there's an extra coefficient, and it's actually 2 times that, because I take twice as many steps. So it's still log n in steps, but it's actually, there's a constant there, which is 2. So this is something we're going to have you implement as like your warm-up CUDA programming assignment before we get into the meat of assignment 3. So you'll be intimately familiar with this. Now, yeah, so I think some interesting things to point out is like it's awesome if you're a theoretician. O of n work, log n steps. But if you look closely, there's an extra, there's a factor of 2 here. There's a factor of 2 here. And there's also some other things that are kind of not great, like you are not using all your processors every single moment. So even though I said let's make use of an infinite number of processors, as the series goes down, you're using fewer and fewer of them every step. And also data is kind of moving around all over the place. So there's some reasons why if I actually asked you to implement this in practice, like in your homework, you're actually just going to do this algorithm. You're not meant to like make it really fast. It's just more of a programming exercise. If you were actually working at NVIDIA and trying to make the library for scan, you would have to work a little bit harder. Okay, and now let's talk about that just a little bit. So now let's think about a simpler problem, actually. Parallelizing this onto 2 cores. Right? So, let's just say we cut it in half. We only had 2 processors and we were running this algorithm. Well, first of all, you have perfect workload balance. That's not a problem. You actually don't have a lot of communication between those processors, which is pretty cool. If you look carefully, look at those red arrows. The only data that ever moves are 2 elements. But you are bouncing around memory all over the place. So even though one processor is doing this side and the other processor is doing the other side, you're bouncing around memory. And I think as you're starting to get in this class, that's probably not such a great idea. Okay? And so in the spirit of doing the simplest thing first, if you gave me 2 threads and said compute a scan, I would probably do something like this. I would divide the array in half. I would do 2 sequential scans, which is O of n, running straight through memory. I would get the base for the first half, and then I would parallelize the application of the base to the second half of the array. If we're on a shared memory multiprocessor, the fact that information computed by P2 has to get over to P1 is not that big of a deal. I'm just reading from the same memory system. Okay? So, the thing that you would do probably in 1 hour if I gave you this as an assignment would probably work pretty well. Yeah. Oh, sorry, I didn't draw my line. Now it's clear. Okay, so let's think about a different type of machine. Let's imagine that you were trying to compute a scan in ISPC, or actually a scan in CUDA, where you kind of know that all of your threads, your workers, are actually operating in SIMD. Okay? So instead of saying I have 2 threads and they're going to be on different cores, or 8 threads are going to be on different cores, just imagine if your workers were SIMD lanes. Okay? So let's take a look at this piece of code. It's written in CUDA, but you can think about it just as ISPC if you want. It really doesn't matter. This is pretty interesting. Look at this. So this is scan. It's called scan warp because this is something that's called by every CUDA thread individually in all the threads in a warp, which sort of share the same instruction stream. Or you can think about this as, if I wrote this as ISPC code, it would be scan of a program, a gang. And so every instance in a gang would be calling this function. Okay. So for now, just imagine that like a bunch of threads are calling this function. And so first of all, every thread computes its lane, which is basically its program ID or your program index. And since, remember last time, your thread index in CUDA could be anything in your thread block. You can make a thread block of 2,000 threads or 256 threads, but those 2,000 threads were going to be running in these little groups of 32 warps. So what I do here, and this is pretty low-level hacky code, is I first compute my ID in the warp, which is to take my thread ID, mod it by 32 to get my actual location in the warp. Okay, so now I'm making assumptions about the underlying implementation. And so then I write basically this 5 lines of code, which says, if my lane is 0, do this. If my lane is 1, do this, and so on and so on. And can you confirm that this code takes 5 steps? So first of all, why is there 5 steps? Log of 32, right? So there's 5 steps, and every step is just an addition of 2 numbers. And based on my thread ID, or my index in this case, some threads stop participating after a while. Okay. So how much work does this do? And log n, right? Like same thing, right? Like in other words, there are 5 instructions. Let's ignore the if statements. Let's just say they're free for a second. There's 5 instructions of actually doing math. That's log 32, and every single one of these sort of lines of code is doing how much work in a warp? It's one thing per thread, and there's 32 threads, so n, O of n total, right? But every thread is doing one thing, but there are n threads. So I'm doing overall n log n work, and my span is 5. Or in other words, like if you put a stopwatch on this program, you would say it gets done in 5 steps. Okay, so what would this code look like if I changed it to use the more advanced O of n algorithm? How many lines would it be? There'd be 5 lines for the upsweep, and then another 5 lines for the downsweep. So, wait a minute, this is weird, right? So my n log n algorithm took 5 cycles. My O of n algorithm takes how many cycles? 10. How can that be the case?
Coefficients.
Well, yeah, the coefficients too, but what happened? Like I'm using the same number of resources, right? I have like this, in some sense I have this SIMD block of execution units that can do 32 things at once. And that 32 things at once takes 5 cycles to do n log n work and 10 cycles to do O of n work. Right? So the fact that the only thing this processor can do is the same instruction. So the fact that I'm doing kind of some redundant work is actually kind of okay. The fact that I did better would mean that I would have all this underutilization of my SIMD lanes. And so I do less work, but I spread it out over multiple sort of highly incoherent instructions. So it's a loss. So you really have to think, if you're implementing a library for scan, is depending on how the parallel work gets mapped to a machine, different approaches may be very different. Like if I'm running on a machine that has thousands of independent processors, I might use that work-efficient formulation. If I'm running on a machine with just 2 processors, I'd probably do the simple thing that you all suggested. Like I divide it in half, compute a scan, move the data over, and then finish this up. If I'm running on a SIMD processor, this n log n thing is actually the best thing to do. Yeah?
So if instead of separating into chunks, with the big O of n implementation,
That's right here?
no,
Okay, let's go back to, yeah, okay.
you split it into between the 8 first and the 8 last limit. if instead we interleave so that like we do A0 and A8 at the same time, it's the same operation. And as long as we have a barrier at the end of each iteration, two threads don't touch the same data.
Well, I think that's the problem that you're solving is not, the problem that I just discussed is a different problem. The problem is the following. Imagine that, like, okay, so this is 16 wide, right? Imagine you had a 16 wide SIMD unit. What are the lanes doing here? There's nothing to do. That's the actual problem, right? Whereas if I had a machine that only had 2 execution, like 2 threads or something like that, the fact that we're not doing much in every step is great because like the processor gets done with the step and then moves on really quickly. Okay. So your work efficiency actually, like whether or not you care about work efficiency or raw parallelism, can actually kind of change based on how the machine works. Okay. And if I was to do this for real, let me go back to, where were we? If I was to do this for real on an NVIDIA chip, for example, I would take that little piece of code that I gave you, this one right here, that can compute the scan of 32 elements in five SIMD steps. And then if I had to do something for, let's say, 128 elements, how would you do it?
7 steps.
We could do the n log n thing, but I'm actually, I would rather not take this n log n. Like I only want to take that n log n asymptotic if I don't have to pay for, I don't have to pay for it in some sense. Like, so what I would do is like, here's what I do. If I have a sequence that one warp can get something done in 5 cycles and I get 128, give me 128 things to do, I'll just have 4 different warps do a 32 wide scan. And now I have 4 partials. Let me just scan those. And then I push the bases back out, and then in parallel I update everything. So, I did this for 128, but imagine you had a 32 squared scan, 1,024 elements. You would do in parallel a bunch of warps, produce 32 scans in 5 cycles. Then you stick those partials together into one 32 wide block, 5 more cycles per scan that, and then take those 32 partials and put them back to the blocks, and then in parallel do that. So it would take 5 cycles to do the original scan, 5 cycles to scan the scans, and then 1 cycle for every thread to add the partial back to itself. So I could do it in 11 cycles for 1,024 elements. And just for kicks, that's the code for doing it. I actually give you this code. You call it as a subroutine if you wish in assignment 3. You don't have to understand how it works. And then if I wanted an even larger scan, I would take my blocks of 32, then do 1,024 by breaking it into blocks of 32, and then I distribute my blocks of 32 across all of the CUDA thread blocks. And I would do that in parallel and then scan those. So I'm actually mixing this data parallel scan with like a more conventional sequential algorithm. So I'm doing data parallel when it helps, or the SIMD when it helps. And then when I have far more parallelism than I have processors, I'm kind of backing off and doing the more conventional thing. So I just wanted to kind of go through that sequence just to let people know that like there's some real sophistication in implementing these data parallel primitives very efficiently on a machine. And I encourage you in assignment 3 to, like, basically we say, hey, learn how to program some CUDA by doing the O of N algorithm. And then you move on to the actual assignment. And I say, by the way, if you have some extra time, why don't you try and make your scan really fast, and here's the CUDA library for scan, and see how close you can get to it. And I have a feeling under the hood they're doing this kind of stuff. I don't know, but it'd be interesting to see if anybody can beat CUDA's standard library function for scan. But as a programmer, you just kind of think, if I call scan, it'll be as fast as a good programmer can make it. You got a question?
So whenever there's an idle link on an idle course, is it still energy?
Probably not so much within a tiny little SIMD block. Let me ask, Kunle, do you think there's any value to, if we were running a SIMD instruction and we knew a lane was dead, do we gate it dynamically? I mean, according to Bill Dally these days with the sparse tensor stuff, yes.
You could.
So I think it's not astronomical savings, but if you're probably trying to save a factor of 1.5 of power or something like that, you probably do. I'm sure NVIDIA chases those types of optimizations. Yeah. Probably the bigger the SIMD width is, probably the more you consider doing something like that. But
you're better off optimizing taking advantage of the wall capability to optimize the use of the
okay. So let's just ramp up the complexity a little bit more, because that's fun, and we're now in the back half of the class. So here's a more interesting primitive. So let's just say we have scan. A very common thing that you might do in applications is you don't deal with sequences, but you might deal with sequences of sequences. So let me give you some examples. Like, for every vertex in a graph, for every edge of that vertex. So I have a sequence of vertices, and for every vertex, I have a sequence of edges, standard graph representation. Or like if you're in scientific computing, for every particle in a simulation, for every particle within some range of it. So it's like a sequence of sequences, right? For every document D in a collection, for each word in D. So I have a sequence of sequences, and the subsequences are all of different length. Okay? So there's kind of two levels of parallelism in these problems. There's sort of the parallelism over the outermost loop, and then there's potentially, if you care, the parallelism over the innermost loop. Right? So imagine, for example, you're running on a GPU and you need 200,000 things. Imagine if you had a graph with 500 vertices, or 1,000, no, that's too small, like 10,000 vertices, but each vertex had on average like 10 to 20 edges. So if you parallelize just over the vertices, you don't have enough parallelism. Right? You need to actually find that parallelism over the edges. So these are the types of problems that fit into this fold. So a segmented scan takes as input a sequence of sequences, and then applies the scan operator in parallel across all of the outer sequences, but applies scan individually to each of them. Right? So what's going on here? This is the plus, so let's take a look. Let's confirm that this is correct. My first sequence is 1 and 2, so the scan exclusive should be 0 and 1, and that's correct, right? Because like the exclusive first element is nothing, that's 0, and the exclusive second element is just everything up to and excluding the second element, so it should just be 1. The exclusive scan here is 0, and then the exclusive scan here is 0, 1, 1 plus 2 is 3, and 3 plus 3 is 6. Okay. So that's segmented scan. And you can think about implementing segmented scan often is you get as input a sequence of sequences might be encoded as two sequences. The first sequence is just a list of, a regular flat list of numbers, and the second sequence might be some binary flags on which one to start, on where the subsequences start. So in this case, the first element is the start of the sequence, and then 1, 2, 3, fourth element is the start of the sequence. So imagine that this was just given to you as an array, and you got that bit flag. You could say, oh, I know the first subsequence starts here, and the second subsequence starts here. It's a very compact representation of a sequence of sequences. If you care about performance and you're doing any graph processing, this is how you implement a graph. It's like these numbers would just be the list of edges, and then you just basically get a number of edges per vertex here in this very common thing. Okay, so we're not going to go over how we implement it, but there is an algorithm, which is really fun to read on your own, that adapts the work-efficient scan that I just showed you and makes it work on sequences of sequences. So you just give it a sequence, and you give it these flags, and the output in O of n time and log n span is that result, the sequences of sequences. And the work-efficient scan looks a little bit like this. Segmented scan looks a little bit like this. The way to understand the algorithm is this figure, which you can think of, it looks really complicated, but really all it is it's the old algorithm, except actually you're just propagating those subsequent start flags along with the information. And what you'll see here is that whenever you need to have a back edge, if there is a start flag, you just skip the propagation of the back edge. So if you go into the code that I had, it basically is, there's some if statements which say if the flag is 1, do something, else don't do something. So it's, if you understand the segmented scan, the regular scan, you actually will understand the segmented scan if you just think about it as with the information I need to pass these flags. And if I ever see a flag, that should stop me from propagating information over a boundary. So it's actually not too big of a deal. Okay. Now, why do we care about segmented scan? Here's a great example. Sparse matrix multiplication, something that we do all the time. And these guys are nodding their heads because they're a big fan of sparse matrix multiplication. So here's a matrix. So here I have a dense vector, my x's, and I have a sparse matrix. And by sparse, I mean most of these values are zeros. Okay? And this is pretty important, right? Like if this was an n-squared matrix and 99% of the values are zeros, I can store it much, much more compactly. And sparse matrices appear everywhere in the world whenever you have sparse connectivity. Like, for example, the way Amazon might store customer recommendation information. I have me, and I have all the products that I have bought. But the cross product of all their users and all of their products would be a very big matrix. But in practice, very few people buy very few products, so they might implement it or represent it sparsely. So one way we can express this sparse matrix is in a format called compressed sparse row. So let's break this down. First of all, it's compressed because we're not going to store all the zeros explicitly. And it's sparse row. So the way this is going to work is I'm going to store all my non-zero values as a sequence of sequences. So if you look carefully, the first row has non-zeros 3 and 1. That's my first subsequence. The next row has a non-zero 2. The next row has a non-zero 4. The last row has 3 non-zeros. So I have my rows are stored as sequences of sequences. Now this is not a sufficient encoding of the matrix because for every non-zero, I need to know what column it's in, right? So I also have, for every non-zero, I have another sequence of sequences that is what column it's in. Right? So, or equivalently, I'm storing for every non-zero, I'm storing a value and a column. And then I have basically an array which tells me in this array where is instead of a bit vector. So before I gave you I'm showing I noticed I just made a skip, a big jump. Okay, so here I use these Boolean flags to tell you where the start of the sequences are. Okay, so if you gave me if I just scan through this array, I get all the starting points. Another way to encode the same information would be, if it's a matrix, for every row, just give me the starting point of the row. So here's what I did here was, since this is a 2D matrix, where is the start of row 0 in this big flat array? Like the subsequence of row 0 starts at 0. The subsequence of row 1 starts at index 2. Subsequence of row 3 starts at index 4. Subsequence of row 4 starts at index 5. Okay? So I'm encoding my sparse matrix as a list of non-zeros, the column index of those non-zeros, and for every row, where does it start in these arrays? So this is commonly called a compressed sparse row format. Compressed sparse rows because it's row major. Like all these data structures are where the rows start. Okay. So if you had segmented scan and map and some other things, let's see how we can do this in terms of our primitives that we have in the lecture so far. Okay, so first of all, given all the non-zeros, I need to multiply them by some x. So for every non-zero, I know the column of the non-zero, right? Because it was down in my columns array. And so I first need to perform an operation that takes all of the x's and produces a list or a sequence that's the same length as my sequence of non-zeros. So I actually haven't told you about an operation called gather, but you should just let's just assume for now that I have the ability to, basically for every column here, I need to make a new sequence that is pulling elements given by this piece of data, the column index, I pull X sub-column index, and I make a new array of X values. So that means that I'm going to be duplicating elements from X into this array. And then I just do a map with the operation multiply. So I need to map every non-zero in values against my gathered array from X. So now I have a product of every non-value. Now I need to sum across the rows, right? So that's a segmented scan with a plus operation. So I have all my products. I can create the flags array that we need to say where's the start of all of the rows. Then segmented scan of this data with this start array gives me all of these partials. And then the last element of every segment is the sum of all of everything in the row. So if I go grab the appropriate values out of this array, I get the sum of everything in the row. So I've done a sparse matrix multiplication that has parallelism proportional to the number of non-zeros, not proportional to the number of rows. And that can be quite cool if my total number of non-zeros is a lot higher than the total number of rows. And this is going to basically parallelize about as fast as map does, no problem, and about as fast as segmented scan does, which is also going to be no problem if we have good implementations of those things. Yeah.
How fast is the gather?
I mean, that could get you a little bit. That could get you a little bit. But you have to do the gather like if you wrote this in like normal C code, you would have to go get that gather. Right? Mm-hmm. The only difference here is that we are actually materializing that gather as a length n dense array and then iterating through the dense array, whereas if we did it with a memory access, we would never create a dense array. We would just go get the data again and again. Mm-hmm. So this just hopefully gives you like a taste of how fun like some of these primitives can be, that you can boil down irregular parallelism. Like now I can have different rows with wildly different numbers of non-zeros per row. I flatten the whole thing and treat it as a big data parallel computation. And that can be pretty cool. That could be pretty cool. Yeah, so I talked about this fictitious gather, and really I should have thrown this up earlier in the slide. Two other really useful operations are gather and scatter. And gather and scatter are your data movement operations when you're thinking data parallel. So let me illustrate these for you. So gather takes an index sequence and a source data sequence and produces an output by for every input element in the input sequence, uses that as the index value, and it grabs the data in order to densify data all over the place. That's what we did for that matrix, the vector X, just a second ago. And then scatter is just the opposite. Given a dense set sequence in memory and a list of indices on where to put it, scatter potentially sparsely the data out to a bigger array. And these can be very costly operations because on one end of the fence, you are definitely moving data to some unpredictable data-dependent place. Okay. These days, actually, on CPUs, you have an actual AVX2, a SIMD instruction, which performs a gather. So that SIMD instruction takes a index vector. So here's a vector register with indices in it. It takes a pointer, membase, and the result of executing the gather is that it will dereference membase sub-index element and bring that data into the result here in the vector register. So in ISPC, when your program just says program index foo does a sub something, that's potentially a gather operation, right? And if you think about how this can be tricky, these are arbitrary indices. It can be whatever they want. So it's very possible for every single lane of the vector to trigger a cache miss on a different cache line. It's very possible for every lane of the vector to trigger a different page fault handler. So this can be a nasty little operation to get right. Okay, so that's why it's very nice that when all of those program instances in ISPC or in CUDA access the adjacent elements of the array, you don't need a gather. You can have a vector load which just says load the 8 elements starting at this base pointer. right? So there's a big difference between vector loads and non-vector loads. There are some fun tricks on, like, it's like I always, when I learned all this stuff, I would kind of go through a lot of this stuff. Like, if you have gather, can you turn it into a scatter? Well, it's pretty easy if the scatter is actually a permutation, right? So if the scatter is a permutation, meaning that all of the indices are unique and they cover everything and they cover all elements of the array, well, scattering according to an index is actually just sorting the data according to the index array. So you might find yourself on platforms where you have a gather but no scatter. And so a common trick is to turn one into the other. Another version, if you don't have scatter, is pretty fun. But let's say you don't have scatter, but you do have sort, map, and segmented scan. So here's a scatter op. So what it means is scatter the value to this location and perform an op. It's actually pretty common if you're doing like a histogram, right? Like you compute a bin that you need to add in, and then you increment 1 to the bin. So look at this. Okay, so for all elements in the sequence, the operation we want to do is for all elements in the sequence, take the index, and I want to put the value into that target location, but not just store it there, like do some op, like take the current value and add the new value into it or something like that. Okay, so let's look at so the first thing I decided to do here is I decided to sort the index array. So I have the list of indices where I need to put those things, and I decided to sort them. And notice that those indices are not unique, so I'm pushing multiple values to the same location. So you can imagine we have a parallel sort. We didn't talk about parallel sort today, but you can imagine that the data parallel library has sort. So now I have the input sorted by the index. So I did a sort of the input data according to those indices. Okay. Now, the next thing is I can compute the start of each range of values with the same index number. So this is my sorted index array. And you could think about doing some form of a map that said, okay, if I am the same as this one, I'm not a start. But if I'm different from this one, I am a start. So you can think about in parallel, figuring out every single element of the array says, am I the start of a new sequence? I just made that bit vector completely in parallel. So imagine a CUDA program which for every element in the vector or in the sequence says, take my thread ID, get the value in my position, get the value in the previous position, and if they're different, I'm the start of the sequence, so return 1, else return 0. Perfectly parallelizable operation. Now, given this sequence, and given this sorted, now perform a segmented scan on that sequence. And now I have all of those operations inserted in the appropriate memory address. Kind of interesting. Oh, and then I guess the last thing I have to do is I would have to scatter the results back out to the target locations. So now I'm starting to do some pretty interesting stuff with just these basic parallel operations. And there are other parallel operations like filter, which is take a sequence, give me there's a function that's a predicate, and remove everything from the sequence that fit that property. Or a common operation in a lot of database-y kind of systems is given a sequence, create a sequence of sequences. So given a sequence of pairs, create a sequence or a sequence of sequences where the subsequences are the key followed by all values with the same key. So imagine the key is a document and the value is a bunch of words. This would be like sort all the words by document. So it's a very common operation in a lot of data processing stuff. Okay, so let's talk about why the heck why being able to think in terms of reducing complex things into these primitives can be quite useful. And I'm going to give you an example that is going to be shockingly similar to your homework assignment. So here's a problem that I took from a physics application. So imagine I have a particle. I'm doing some galaxy simulation or something like that, and I have all these particles representing stars, or I'm doing a fluid simulation. I'm representing fluid by particles. So in this case, I have a bunch of particles that are red dots, and the name of the game is I want to create a data structure where, okay, right, and then I've divided space up into 16 cells. So there's a grid over all of space, 16 cells, 4 by 4 grid. And then I have all these particles at arbitrary locations x, y. And what I want to do is I want to create a data structure where for every grid cell, basically this table over here, for every grid cell, I create a list of particles that are in that cell. So in some sense, this is a sequence of sequences, right? The outer sequence is of link 16 and has cells. The inner sequences are the number of the particle IDs in each cell. So that's what we want to create. I want to create a sequence of sequences or a grid of lists. That's the data structure. And I'd like to create this data structure completely in parallel, assuming that I have tons of processors, a lot of particles, but maybe not a lot of grid cells. The reason why this is a cool problem is this data structure is super helpful for any kind of physics simulation when you want to say, I want to compute the forces on this particle based on nearby particles. And then what you might do is you say, oh, well, if I'm in this cell, give me only the neighboring cells, and I'm only going to iterate over those particles. So it's a common n-body simulation kind of task. So they have to make these data structures all the time. Okay, so let's think about the dumbest, well, not dumb, that's probably exactly what I would start with, right? Probably the smartest first implementation, which is this. For every particle in P, let's assume there's millions of particles, compute the cell containing P, and let's just say I have a lock or something like that. Take the lock on the cell, take the global lock and append P to the cell list C. Pretty straightforward solution. What are performance problems with my solution? First of all, do I have a lot of parallelism? I have tons of, I have tons of parallelism over particles. That's true. I can parallelize that for loop. But do I really have a lot of parallelism? People are saying no. Why not? Because like this parallel loop is basically going to synchronize on this lock. Absolutely. Okay. How do I make things a little better? So I have contention on a shared thing. It's the shared lock. How do we alleviate contention?
Yeah. I mean, you can just duplicate that cell list, like in dimension that might have that kind of reduce it.
Okay, so one suggestion would be I'm going to make a different cell list for every particle, for every thread, excuse me, and then we'll just in parallel deal with all the different cell lists. Now in this case, this is for each particle in parallel. So are you going to make a different cell list per particle?
Like you just make and you just the block
for every worker thread on the machine, let's make a different cell list. That's a good approach. So what are the costs of that?
You have to have all those cell lists and you send them.
I have to allocate all the stereo lists, and then I'm going to have some merge process at the end. And so if we were running on a machine that only had a small number of processors or small number of threads, I love your solution. Looking good. If we were on a machine that had a ton of processors, maybe creating 10,000 cell lists is not tractable. And then maybe actually even merging those is going to be a good fraction of execution time. Without dramatically changing the code, are there any other options? We have contention for a shared lock. Okay, so one thing we could do is have a lock for every individual cell, right? Because if I want to update the data structure in the cell, I'm not going to collide with people touching other cells. So I could at least get 16 times less contention here. Maybe that will work, maybe it won't. Or it'll certainly work with small number of processors. For a large number of processors, it may not work, because there'll still be contention for these locks. Like, say I have 100,000 CUDA threads trying to grab 16 locks. That could be a problem. Okay, so we have massive contention with you saw. And you told me already that we could actually move to a list of different locks, or start to multiple different locks. You also suggested that if we have a small number of threads, I don't quite have I do have a slide on that, but it comes later, is we could just duplicate the data structure. But again, both of these solutions are probably not going to scale to hundreds of thousands of threads. Okay. If we wanted to scale to hundreds of thousands of threads, any other ideas?
Probably something like we did earlier, with sequences of sequences.
Yeah, we're going to have to go data parallel, but I want to hear, yeah.
I was just saying, if they're all like equally, can we just statically divvy up the cell list?
Well, there's only 16 cell lists, right? So one interesting take here, by the way, not a great solution, but I actually could change the axis of parallelism. I could say I'm going to parallelize over all the cell lists, and for each cell list, I'm going to iterate over all the particles, and if that particle is within me, I'm just going to add to my own cell list. Notice how there's no contention at all now. What's my problem here? Well, one problem is I've defined this thing to say there's only 16 cells, so that's not enough parallelism. But there's actually an even more frightening thing. What if I actually had 10,000 cells? I might be feeling good about myself. But is there a problem?
You're just over data.
Every thread on a unique cell is basically doing the whole problem. It's looping over all p particles. Okay. So that's trouble. And then a fourth answer was the one that you all gave me, which was we could duplicate the cell list into multiple cell lists and merge them at the end, which I also thought was a good solution. But again, like I don't think any of these, the ones you're offering, the ones I offered, none of us is going to get us to a good solution with 100,000 threads. Okay. All right, so let's think about how to do this in terms of data parallel concepts. Okay, so let's start here, and let me just show you some data representations. Let's say that we have particle indices. Those are my red numbers. So that's like particle 0, 1, 2, 3, 4, 5. That's what I'm right here. Now imagine I run a map on every particle and compute what cell it lies in. That's an easy computation, right? If you give me the xy of a particle, I can give you the cell. And the results of that map are now represented here in the sequence grid cell. So now I know I have these particles need to go into these cells. No communication, that's pretty trivial.
And just group by on that?
Yeah, so we're getting there, right? Yeah, so how are we going to implement this group by? And now I'm not going to give you group by. I'm thinking about like, well, you could just group by on this, but now I want to do it really, really fast. So let's think about what is a really good implementation of group by, okay? And to do a really good implementation of group by, we need that to be parallel. Okay. So grouping and sorting are kind of the same thing. So let's invoke a really high-performance sort. Okay. So now we're going to sort all of the indices by the grid cell. So I did a sort here based on, I sorted the array grid cells, which if you look at the grid cell, you get this. But also notice that I kept the particle index with it, because I need to know that this particle 3 goes into grid cell 4, and particle 5 goes into grid cell. So I've essentially done a group by via a sort, right? But my goal is to have this data structure, not just kind of there. Okay. So now I need to figure out where are the starts of the bins. Because I don't have a sequence of sequences right now. I just have a sorted sequence. So I need to find the starts of the bins, or the starts of the subsequences. How do I do that? I've told you. Yeah, so I could run a map on this code and say, if my value is different from my neighbor's, I'm the start of the sequence. Okay. All right, so I'm going to run that code, and just trust me that that's what this is, because it's starting to run out of time. And so I'm writing basically, if I at index, foo, if that value is different from the left, then my position in the array is where the start of bin foo is. So I'll let you kind of take a look at this maybe offline. But at the end of the day, I end up with these cell starts and cell ends. So my goal here is, this is an array of 16 values. And this code updates some of those values based on whether or not the current thread is looking at an element that's the start of the bin or not. Okay. So what I've done is I've done a map, a sort, another map, and I have my data structure. So just confirm that this is the data structure. So this is a data structure that says if you give me a cell, 0, 1, 2, 3, 4, 5, whatever, if I look up there, I look up the cell start and the cell end into the original particle array. Okay, and just from the diagram, the reason why most of these cells are empty are because in my problem, most of the cells are empty. Okay. So it's a completely data parallel way of making a uniform grid where your parallelism is proportional to the number of particles and not the number of cells. Now, Ron Fenko, who in the back, probably had his students do this a bunch of times because he loves to have particle lists hanging around. Give me a particle, tell me what's next to it. Okay. Now, I'm going to stop. We're basically done. I'll actually give you a couple of minutes back. But the rest of this lecture, which I did not plan to get to, these slides are here only for your reference, is some fun stuff of how do you make a histogram with only these primitives. So here's a way to make a histogram. And I think going over this histogram example is pretty helpful, actually, because you have to count the bins and do other things. Yep.
What you did before it would be a pseudo.
Pretty close. Pretty close. Yeah. Like histogram is about the same. Yeah. But you'll use this in your. The only difference between the histogram and what I just did is I found all of the particles that go into the same bin. Yeah. The histogram needs to actually finish it off with a segmented sum to actually compute the total sum of those things. It's more like the sparse matrix multiply example I gave you. Mm-hmm. And when you're doing the segmented scan, you got to be a little careful because some of your bins can be empty. So there's a special case in here for what happens when you have empty bins. Okay. Anyways, point of the day is there's just kind of a whole other way to think about parallel algorithms, which is how do I reduce irregular data structures, irregular parallelism, to regular parallelism that's sort of embedded, encapsulated in some library of these data parallel operators. And depending on your platform, you will have different libraries. So, for example, if you're programming a GPU, NVIDIA has implemented this library called Thrust. And just go Google it and go look at the API documentation. You will find things that look very familiar given these lectures. It's map, it's sort, it's scan, it's segmented scan, it's all of these things. And if you don't really want to do crazy CUDA hacking, you can just express your algorithm in terms of those high-level primitives. All of Apache Spark, which you may have heard of for distributed programming, is based on the idea that all of your Spark programs are done in terms of these sequence operators. Their sequences are called these RDDs. An RDD is a sequence. And they only give you this set of operations to do things on RDDs. And the whole premise of Spark is that if you use these RDDs, you get parallelism across a cluster, you get fault tolerance and redundancy, and these operations are enough to do a whole bunch of cool data analytics. And so that's why Spark got so popular. But just different implementation, basically the same idea as this Thrust. So you'll get a little bit used to this in programming assignment 3. All right? Okay, good luck finishing up 2, and we'll be shipping you assignment on Monday.